So this is Friday Night at Cary. I'm Bill Schlesinger, president of the Institute. Welcome back. Many old friends out here tonight on a wet night, but what a better night to forsake the family barbecue and come and hear something about nature in dry conditions. We've got a double treat tonight, two speakers in one, talking about a new book, which I just had a minute ago, Bug Music. How insects gave us rhythm and noise should prove to be an interesting evening. Our first speaker is going to be John Cooley from University of Connecticut, where he's an entomologist, one that studies insects, a graduate of Yale as an undergrad. I don't hold that against him, and University of Michigan as a PhD. Has been in the news widely in the last couple of weeks because of the cicada outbreak in the eastern U.S. I just picked up and took my copy of Nature to lunch today, and settled down to eat my burger and read about the latest science. And there was a feature article on cicadas with a lot of coverage of John in that, and it's been on NPR and a number of other places all across the country. Their timing of the book and the outbreak, perfect. After John gives us a little bit of a warm-up from the point of view of a professional entomologist, we have David Rothenberg, who is a professor of philosophy and music at the New Jersey Institute of Technology, a graduate of Harvard. I won't hold that against him either. I'm a Dartmouth guy, that's the problem here. And Boston University, where he got his PhD, has been intrigued with music, both made by humans and made by birds and bugs throughout his life, with studies both across North America and in Europe. He has been called, his studies of animal song and experiments with animal noise has allowed him, in that great source of all information here that I consulted this morning, namely Wikipedia, that he's called an interspecies musician, which I think is a wonderful title. I hope you have that on your business card. And they're going to tell us, basically, I mean, we got all kinds of history here at Cary listening to bird song. In fact, we have Ken Schmidt here from Texas Tech with his field crew this summer, studying bird song among other aspects of birds. But I think we have much less appreciation as a country, as a citizenship, on the noises of insects, what they mean, how they may have evolved, what they communicate. I think we're going to learn a lot about that tonight. As usual, courtesy and arranged by Merritt Bookstore, there is availability of books and book signing after the lecture. But for right now, let's start with John Cooley, Bug Music.
Thank you very much. It is a real pleasure to be back at the Cary Institute. I'm actually an alum of the REU program here many, many moons ago. So I am very pleased to be here tonight to talk to you about what I know. And so the way we're going to do this is I'm going to give you a little bit of a scientific discussion of the periodical cicadas, tell you how they make their sounds, why they make their sounds, and then David's going to take it from there. Now, this is an Institute of Ecosystem Studies. There is an ecological component to this research. I'm not actually going to talk about it tonight, except to give you two slides. I'm going to say this is the distribution right here of 17-year cicadas in eastern North America. It's not just New York. It's not just the eastern seaboard. Almost every year, somewhere in eastern North America, you can see 17-year cicadas. It just happens that this year you see them along the eastern seaboard, so we get a lot of press and a lot of attention. This is the ecological component. We've been doing niche modeling of the periodical cicadas to try to understand a little bit more about what affects their distributions. And I'm not going to talk about that tonight, but I felt obligated to put up a slide of the ecological part of this research. And by all means, if you want to hear about it afterwards, and you're not sick of cicadas, come find me and I'll be happy to talk about it. Instead, I'm going to talk a little bit about what these cicadas are doing. So here are periodical cicadas. They emerge in large numbers every 17 years in any given area. Now they don't seem to be right here. That's kind of the ecological component. But if you go down a little bit into the Hudson Valley, you'll get into some pretty good choruses of periodical cicadas. Now periodical cicadas come onto the radar of Europeans and Western peoples in the 1600s. Colonists in Massachusetts encountered them very early on. What do you think they thought when these cicadas came out? Deadly plague of locusts. They're not locusts. They're not a plague. They're not deadly. They're not harmful. None of those things. But in North America, the name locust has stuck. Locusts are grasshoppers. These are cicadas. But nonetheless, we call them locusts. 17-year locusts. Now, the formal scientific study of periodical cicadas really began in the 19th century. Some great work by Charles Valentine Riley and Charles Marlatt. And they began compiling records and information and maps and putting it all together to figure out that these cicadas have life cycles of 13 or 17 years, and different regions are on different emergence cycles. So they're all running along on different schedules. Nonetheless, we still have this problem. We've seen a lot of press this year about Swarmageddon and things like that. And here's the Chicago Tribune: pests, problems, diseases. It's none of the above. What I want you to walk out of here tonight knowing is that these are some of the most marvelous and intriguing insects on the planet. And I'm going to talk about what all that noise they make is about. Now, all cicadas, periodical or not, and there are roughly 5,000 species of cicadas on this planet. Only 7 of them are periodical cicadas, and they're only found in the eastern U.S. All cicadas, though, do this. They spend most of their lives underground. Large number of years. For most cicadas, we don't know how many years. It's a significant number of years. Underground, feeding on roots as nymphs. And then when it's time for them to come out, they exit. They make an exit hole and they crawl above ground. Now these are insects, so when they grow, they have to molt. And so this nymph is going to crawl to some kind of a surface, an upright surface, tree trunk, fence post, you name it, and it's going to molt. And this is the molting process, and we call this individual a white. It's a white cicada. It has just molted, and it will be that creamy white color for about an hour. After that, it will have its adult coloration, a black body with red eyes, and you'll have this mess below your trees. And those are the shed skins, the dead cicadas, the ones that didn't make it. That's what's left behind. The ecologists out there, I want you to be thinking about resource pulses and all that kind of stuff, because it really is a real phenomenon here. That's a big effect on the ecosystem. So after they molt, they leave that behind, and they go into the trees and they begin to chorus or make sounds. One of the things you may not have known about cicadas is that only half of the individuals out there are making these loud sounds. And those are the males. So males have a pair of sound production organs on the first abdominal segment. Look like a little ridged potato chip. This organ is called a timbal, and it vibrates and it makes a sound. The abdomen is hollow, amplifies that sound, and the sound radiates out from 2 openings on the underside of the insect. Now, as an acoustical biologist, I like to picture sound in 2 different ways. A sonogram is a chart of sound pitch over time. So the vertical axis is pitch, horizontal axis is time. And I also think about sound as an oscillogram, or a chart of sound energy over time. And so this cicada right here is Ochanogona canadensis. It's a northern cicada, or at least that's what the literature said. It turns out you can find it in Virginia, so it can't be that northern. But this is Ochanogona canadensis, and it has a sound that's just kind of a little lispy trill. So I'll play that sound. And that cicada will sit in a treetop and do that all day long as it's sunny. Now, it turns out that cicadas are really great to do playback experiments with. We can record those sounds and play them through speakers, and we can see what happens when we play recorded sounds to cicadas. Now, it's a long story, but it turns out that my colleague David Marshall and I discovered by playing around with cicadas and doing playback experiments that, while only the males make those loud sounds, females also make sounds. Now, they don't have the organs, the tymbals, that the males use to make their sounds, so females make their sounds by clicking their wings and make a little tick. So here's Cicada, a New Zealand cicada species. Little buzz, and if you look at an oscillogram of those sounds, those loud sounds are the male pulses, and right in between there is a female wing flick. That's a duet. Cicadas engage in duets, and after these duets, they mate. So it's an unusually complex form of courtship for an insect. This is a periodical cicada, Cicada septendecim. It's the one common in the Hudson Valley. It has a pure tone call with a down slur. And there's the female click right afterwards. So, click. And that's the duet that males and females engage in. Once they duet like that, they go through a series of different courtship songs. So, court 1 call. Female responds. Then the male will go to a court 2 call. She'll respond. He'll do a court 3 call. And they'll mate. Very, very complex courtship. And when you're walking out there in the choruses, you're hearing a mash of all those different sounds. Turns out you can imitate those sounds, and we'll try that at the end, not during this lecture. It really won't work. But you can imitate those sounds. This is a clip from David Attenborough in Life in the Undergrowth. He's clicking his fingers to imitate a female and duet with this male. And it turns out this right here, this light switch, is also a very good device for imitating a female wing flick. So we'll play around with that a little bit at the end. There are 2 life cycles in Cicada, 13 and 17 years. There are 3 species groups, Decim, Cassini, and Decula, and they all have distinctive sounds. So Decim is. Cassini is a series of ticks with a frequency sweep. And you will hear those down in the Hudson Valley. And the Decula species are a more complex call. Apparently you'll hear some of those around the Hudson Valley too. They're a little bit rare. So we have these different species groups, and we have 7 species total. 3 with a 17-year life cycle, and 4 with a 13-year life cycle. The last thing I want to say about periodical cicadas before turning them over this over to David is that you can see we have a very complex species problem here. We have life cycles, we have species groups. It's a real mess for an evolutionary biologist. But I haven't even talked about this, the broods. Different parts of the country are on different cycles. And we call all the cicadas that are emerging in a given year in a localized area, we call that a brood. This is the year for brood 2. It's getting a lot of press because it involves New York City. But last year, brood 1 was out down in the Shenandoah Valley. And next year, brood 3 will be out in western Illinois and in Iowa. So almost every year, you can go out and find periodical cicadas somewhere. There are 13-year cicadas as well, so you can see there's a very, very complex mix of broods and species and life cycles. Charles Marlatt compiled the brood maps most of the maps that are circulating today are based on. And when you look at Marlatt's maps, you see these broods are like puzzle pieces. They fit together, but they don't really overlap. There's a problem, though. If you look in detail at Marlat's maps, this is his map of Brood 1, the Shenandoah Valley brood. And you see, okay, there are records in the Shenandoah Valley. There are all those ones east, down on the Piedmont as well. And there are these ones in Indiana and Illinois and Kansas. So Marlat's maps are groundbreaking, but they're difficult to work with. And if you go out today and look in Kansas and don't find cicadas, does that mean the brood changed? Or does it just mean there's something wrong with Marlat's maps? Chris Simon at the University of Connecticut tried to address that problem by updating the maps, and she put some maps out in 1988 that revised Marlat's maps. And Chris Simon's maps are very good. But they're not geo-referenced maps. These are not dots that you can go visit. And they don't represent localities where you can go back to field notes and see what was at that spot back in the day. So we have a project here, and there's some cards for the project out on the table, and I encourage you to take them and participate. This is citizen science. We have a project to remap the periodical cicada broods using GIS technology and the internet and all the tools available to us. And it's been a very good project. We've been able to publish a lot of interesting papers. We started out just by making dots on maps and transcribing them later on, but now we have a website and even a little app for your smartphone. Go out to where the cicadas are, call up this app and push some buttons and make a report. These maps are important. Your information that you send us tells us what's happening in real time with the periodical cicadas, and then we can send researchers out to go and confirm and figure out what's going on. So we can do rapid surveys using the cicada mobile. I broke it down in a garage, but the cicada mobile has lots of distinctive features, most of which is all the dead bugs under the front seat because they blow in the windows. I'm the only guy in the world who drives up and down the highway with the air conditioning on full blast and the windows all the way down so I can hear. Very hard on the vehicle. Now, why is this important? Why are we interested in remapping these broods? One of the reasons, and I want to encourage you to be involved for this reason, is that maybe the periodical cicadas are a little bit like passenger pigeons. Back in the 19th century, people said, oh, passenger pigeons, there's so many of them. We don't need to worry about conserving these. Nothing will ever happen to them because there are so many of them. They darken the skies. Well, here we are, beginning in the 21st century. There are lots of periodical cicadas. They don't quite darken the skies, but they fill our ears. Well, we need to worry about them. These insects, just like passenger pigeons, rely on dense populations to survive. And if something happens to the density of those populations, if something happens to the numbers of cicadas out there, these populations crash fast. We don't really understand that. And the reason is we don't have good maps to go back to and find out what these emergences were like in the past and compare that to what we see in the present. So that's why we encourage all of you to get involved with the citizen science part of this project. Send us your reports of periodical cicadas and help us build a map so that in 2030, we can come back and tell you whether Brood 2 has changed. So I'm going to end it there and turn it over to David. I'm happy to answer questions later on. And at the end of this, we'll kind of cut into a more free-form thing and try to get these cicadas here to perform. Thank you. The rubber.
Hello, is it working? Sounds promising. Okay. All right. Thank you, John, for introducing introducing the amazing discoveries you've made, these creatures, and I'm going to explain to you why anyone might think what cicadas are doing has anything to do with music whatsoever. And this is the third book I've written connecting music to animals. And I think to understand why you might even make such a connection, I'd like to begin with birds. About 13 years ago, this is the moment, 6 a.m. at the National Aviary in Pittsburgh, where I got the idea that maybe there was a good story here or something you could do playing music with birds. What kind of bird is it? Anybody know? Thanks. What kind of bird? Not quite. A white-crested laughing thrush. Later I learned why a laughing thrush is one of the best birds to jam with, because the males and females sing very complicated duets. Cicadas sing duets, but you can barely perceive that they're happening. Male and female laughing thrushes each know a whole series of phrases, and they kind of go back and forth. So the males aren't just singing to advertise themselves, that's what usually happens, but there's a kind of back and forth between the sexes. And you wouldn't really notice this is interesting unless you wander around the aviary with the clarinet. There's only 2 papers ever written on this phenomenon. And so this made me think that maybe you could use music to try and understand something about the natural world. Later, and I wrote a book about this, Why Birds Sing, that shows what scientists, poets, musicians, composers, and naturalists say about birdsong, and how they all say different things and have the best human understanding of a phenomenon in nature. You have to use all the tools we have at our disposal. No one approach is complete. Next, I thought I'd try the same thing with whales, which was interesting because nobody really knew about whale song until the 1960s. So you can trace what happened when people found out about this. And it's a little harder to do because the whales are underwater, but you get the sense of what's involved here. I'm broadcasting my sound underwater and listening to what the whales are doing, trying to engage. Most of the time they ignore you, like a lot of creatures in the world. Why should they be interested in us? This is a diagram of how to make music with a whale, in case you're interested. It is against the law, by the way. According to the Marine Mammal Protection Act, you're not allowed to harass marine mammals. Unless you're a scientist and have a permit, then you can do anything to them, kill them, dismember them. Or if you're a Japanese whaler, then you're allowed to. But here's maybe the most interesting interaction between clarinet and whale that I recorded. We didn't unfortunately film this, but I recorded it. Again, most of the time they ignore you, but sometimes they show some interest. If you study sonograms of this, you see the whales are doing things they wouldn't otherwise do. I also have to note that unlike with insects, playback experiments with humpback whales have been very inconclusive, playing them back their own song. They don't respond that much. They seem somewhat interested in the clarinet sometimes. Now, if you try this with cicadas, there's certain hazards that might come up. There's just as many inside the shirt and inside the pants. You can try this out here. I haven't seen quite this many anywhere except this moment at Lake Springfield, Illinois. This is like the epicenter of Route 19. So, this is how it began. I thought, well, this would probably be a crazy idea. Hell, so, but you might think this is ridiculous. And yet, people actually love insect sounds. They've appreciated the beauty of them for hundreds and thousands of years. Here's a painting by Charles Birchfield, a somewhat well-known American artist from Buffalo. And this painting is called The Insect Chorus, and he's trying to sort of graphically illustrate just how beautiful all these sounds are coming from bugs, different places. And it comes along with a legend where he's saying which species are making which sounds. Some are in these high trees, some are close to the ground. He's kind of abstractly illustrating what's going on. Fireflies have been, praised for, more is probably talked about them by science and in probably outside science as well, because you can see the rhythms, you can see the patterns. And so people have recognized there's some kind of synchronization going on, that it's not a random phenomenon. And the same with the sounds of many insects. And for example, certain species of crickets, without each individual knowing very much, they're able to synchronize all together by just adjusting the sound that they make. They hear the one that's nearest to them, and they get their sound a little bit closer to it, just a little bit. And it then synchronizes. This is a model by Michael Greenfield explaining, play models of how you can, how this comes back together. And we made a little kind of simulation of how this works, which has a lot of numbers. Well, I'll show it to you anyway, because it's kind of cool. So let's get this is simulated insects. They're following that model. Does it in fact work? Let's see what happens. They're starting like 4 seconds apart, which is more than they ever would. Each one's now listening to one insect, the first one, and gradually adjusting its rhythm to all come together. If you want to try this, you can download it from the website that goes with this book. Bugmusicbook.com has this little thing you can try out. So after a little while, you get to this sound of the snowy tree cricket. They get all synchronized. And so you often hear this, you can hear it in the meadows and forests around here. And what I want to show you now, I've made a piece of music just based on that sound. Everything you hear comes from that sound. And I want you to see it, because we talked about sonograms, and sonograms are turn sound into picture. And this is kind of necessary for science to be able to analyze sound and take it seriously. Before this was invented, there wasn't that much really quantified, careful work on sound. And you could also, however, use sonograms like a musical score. And this vertical axis is showing frequency, high notes and low notes, and the bottom just shows time. And so you're going to listen to this piece, which is all made out of that sound you just heard, and the sound's been transposed, it's been looped, it's kind of delayed, and I'm going to use this as a kind of musical background for what I'm going to play. And you can read the score here, see if it makes any sense. Turn this off. So when I was working on this project, writing a book, I then also made a recording where I did a lot of the music live with insects, and then also took things like this, took their sounds, and kind of played around with them to make insect-inspired music. And you have to wonder, like, well, is this some sort of new thing that we can just do with technology, mixing human sounds with insect sounds? Actually, no. It's really going on all over the world. Here's a recording and a sonogram of women singing in the Ituri forest, Bobenzeli pygmies, a recording made by Louis Sarno, who spent about 40 years living with pygmies in Central African Republic. And this sonogram shows what we're about to listen to. And when you look at this image, now that you see how the sonogram works and listen, you can see that this reveals different frequencies, different places in the sound spectrum in a kind of organized way. People are singing along with all the creatures that live in their environment. So whether by accident or design, you have people who found a way to sing their way into the soundscape. A cicada singing alone might just sound like noise. Actually, it's a very complex, rich, and organized sound. Here's a different species of cicada. John knows which one. And just look how beautiful the sonogram is, and hear the noise. You hear it's very precise kind of noise. Defend their territory, say, this is my place. This is the function of this kind of song. But if that explanation is enough for you, you're missing what's really going on, because the function is not the same as what's actually being done. The function is the same all throughout the animal world. The difference is in the music, is in the shape, in the form of the sound, in the aesthetic, really, something that Charles Darwin realized very well when he wrote in Descent of Man. Birds have a natural aesthetic sense. They appreciate beauty. That's why they've evolved beautiful feathers and beautiful souls. It's not an unscientific idea to think there's music in nature. Skipping some things here. Here is my friend Tim Hill. He's an overtone singer. He can sing many sounds at once, like people in Mongolia and Tibet, and he sings all kinds of chords together. So I took him out to Glenwood Farm. We were singing at night. We were playing around I had him singing along with all the night singing insects. The sonogram sort of shows some kind of pygmy-like relationship. can see that this demonstrates the cicadas' slight interest and response to sound is very different than their own. But I think they respond to all kinds of ranges of frequencies and just a general mood of noise they can tap into. And this is, Cooley doesn't like this map, he made it. I like it because it has all these different colors and it tells you what year you can hear them when. So if you get addicted to these creatures, you know where to find them every year somewhere. And especially in 2018, you can go to find a brood 7 that pretty much only comes out in Onondaga Reservation territory in upstate New York. Onondaga will tell you that in the 19th century, the cicadas saved their people from famine. And, or you're saying starvation, they were starved by the white people. And here's our brood here, various maps. There is the master out there in his preferred research uniform, a tie-dye shirt. Notice the details of the cicada mobile. It's got all kinds of data entry devices. What is the gold knob there? That's the shifter just made it exciting. It probably shifts the cicada sound.
The other one banged into the handle there. The one that came with the car. It's got an angle to it.
Yeah. Okay. So there are many theories as to why the prime number cycles. One theory that I like the most, I wrote about in the book, is that in times of uneven glaciation, there might be just some concentrated areas that were green, the rest is surrounded by snow and ice, and the cicadas might be breeding very intensely, and they all go down to underground, one concentrated area, just to see what years they might come up. 2, 3, 4, 5, 6, 7 years. They might hybridize with other ones. This is a totally theoretical model. And these Japanese scientists came up, they said, if you run this model, just testing it out, prime numbers would win out after a few hundred years. And nobody knows if this really works, but the model suggests that this might happen this way. A more common explanation that's well known, because Stephen Jay Gould wrote about it, is that they have prime number cycles and predators that might eat them have non-prime number cycles. So I'm not sure such predators and these cicadas actually exist. And it also doesn't suggest why this might happen. Only in the eastern United States, nowhere else in the world is possible to have uneven glaciation. But they're all just theories, and none of these cycles is complete. And yet, the whole idea of the 17 years, the 13 years, numerology of cicadas is investigated. You've seen the life cycle. Here is an imitation of David Attenborough's watching the cicadas on a branch. It was just clicking so much that it was bothering me. Maybe I'll just try and shout. And then what I want to shout out to you right now is each species has this different sound. And there's two main ones we're hearing around here, septimdecim and cassinine. And what interests me is that they have a different musical way of operating. And that the septimdecim, each one makes this pharaoh sound you can hear from the cage over there. Pharaoh, pharaoh. And yet, if you hear millions of them, all you hear is, how does that work? And it turns out that the tail sort of drops up off into like another frequency. You have this distant fuzzy chord. And so to demonstrate how that works here, I just took one sample of that sound and copied it over and over again, multiplied it, to see if it's really true that actually happens. They're really loud, you'll hear more of those in the afternoon. And yet they synchronize in a way related to the crickets that I demonstrated earlier. When it gets really warm, there's a lot of them, they'll synchronize in waves. Like a wave, And why do they do this? We don't know, but I hear these two things as kind of different musical strategies. ways of all gathering together. Let's see, we're seeing the demonstration. You want to hear these sounds again? The great Cooley Marshall discovery. I think this is like the greatest thing. These guys figured this out. There we have the basic call. We call that court call, right? A female wing flick. And then we flip to this. Another one of these. And then another wing flick here. And then court 2. Very nice. Simulated wing flick. Time for mating. Any other insect has so acoustically complex a series of sounds it makes between male and female? I don't think so. I don't know, but it's an amazing, several amazing things about this. That one is that how come nobody ever noticed this before? For decades, just said only the males are making sound, only the males are making sound. And then it's not that hard to see once you know to look for it. And once you listen more carefully, you start to hear all these different sounds. So in a way, there's an aspect of acoustic science that it's really deciding there's something worth listening to. Until you decide there's more to hear, you won't hear it. Which goes back to the story of humpback whales. You know, humpback whales sing underwater. And when the Navy invented microphones that go underwater, that's when people were able to hear this. That's the standard story. However, if you go diving in Hawaii, you hear it right away. You only have to be a little bit underwater. You hear these humpback whales. Why did no one hear it? There's nothing written about this anywhere in the world until people thought to listen. So a lot of paying attention to nature is just deciding that it's worth paying attention. And you can hear and find all kinds of things. So I think because of time, we'll stop there. We can have some questions. And so, number one, this is an amazing discovery. Marshall Band, we should give him a big hand. I really believe that the whole citizen science aspect shows that people can really help this research just by noticing where the cicadas are. Because it's hard for the one cicada mobile, in fact, it's compromised. It's now being fixed somewhere. The government does not have a department of cicada studies ready to send out agents to collect this information. It's up to you. Only you can help figure out what's going on. The magic cicada, a very magical creature. And I think that, nobody can quite explain why there's so much interest in these cicadas this year. Like all this coverage of this story, it's kind of shocking. But I think people are really interested in the fact of some wondrous thing that occurs in our midst. One of the pioneering entomologists, H.A. Allard, in 1921, he was writing about the 1920 emergence. He wrote very poetically that he felt like he was experiencing one of the great moments in his life, like the revival of the great current, something that we will hardly ever experience. It's right around us. We should all go hear it. And you can go back a few hundred years to the haiku poet Basho in Japan, who wrote, "Cicadas sing, know not how soon they all will die." Thank you very much.
Questions for both, or are we going to get these guys jazzed up?
Questions? Whatever. Questions?
Let's field a few questions, then we'll try a little demo here. Why not? We'll walk on the wild side with the insects.
I'm way in the back there, red shirt.
I was wondering, Dave, at the hospital, a nurse said to me if I didn't hear cicadas already, I wouldn't hear them. Is that kind of what it means?
I would say, having watched the emergence and looking at the progress of it, that most areas of Brood 2 should already be seeing significant numbers of cicadas out, and I would be surprised if there were large pockets still to emerge. I think this is starting to get towards the late phase.
So will we have singing for another week or two?
You will, now that I think most of them are out, you can expect the singing to last a couple more weeks. Everyone always asks, how long do they live? And the answer is 17 years. But what they're really asking is how long do the adults live? And the adults live 3 to 4 weeks, depending on the weather. This business going on outside right now is not going to help. It's going to knock a lot of them down, and the mice and birds and ants are going to get them. So this is not a good thing for cicadas.
I'm interested in how do they synchronize these wave-like sounds? Do they have ears? And if a whole bunch of us all went out with a whole bunch of cicadas there and did that wave-like sound,
We'd be just one, you know, we'd be a few voices in the millions, you know. So we just a few voices in millions of other voices. We can get into the mix, but we're not going to transform it all. We're just another singer. Shh. There's 10 of us, you know. They might start to respond, but there's so many others there.
well, I'm hoping that you could leave us in a little bit of that.
We can do that, yeah.
I mean, I think we'll get into that when we demo these guys, and I'll talk a little bit about that.
But do they have ears?
Oh, yes.
They do.
They have excellent ears, and they're very good at hearing each other. And we're going to try to take advantage of that to get these guys to perform for us.
Right here.
Why are they most active in the sunshine? Well, that's a very good question. They are insects. In the old days, they used to tell us in intro bio that they're cold-blooded animals and all that kind of business. Well, it turns out they don't really have blood, so there's a problem there. And they also are very endothermic. They generate their own heat when they're active. But the catch is they're not like us. They don't have a basal body temperature. So in the morning, or on a horrible cold rainy day like this, they have a very hard time getting going. They need to have a minimum body temperature to be able to contract the muscles to fly, to walk, or to make those sounds. And so they are black bodies. They get out in the morning and bask in the sun, and they warm themselves up and get going. So that's a simple answer to why they're most active on those sunny, hot days.
Yep.
Female lays eggs and twigs, and I've seen the leftover twigs. She lays them, she must lay them in a clean twig. And how long does it take before the egg hatches, goes out, which then falls to the ground 30 feet or whatever it is?
Very, very good question. Periodical cicadas are interesting because the females lay their eggs in live twigs. Other cicadas will lay in bark and dead twigs and whatnot. These lay in live twigs that are about the size of a pencil. And the female will excavate an egg nest, a little fork-shaped structure, and she'll put about 30 eggs into each one of those, 600 eggs over her lifetime. Those eggs will hatch 6 to 8 weeks later, depending on the weather. And when they hatch, the nymphs will fall to the ground and go into the soil and start feeding and start the cycle over again. And the hatching nymphs are tiny, the size of a small ant.
It looks like a zipper.
Yes, the egg nests do look like a zipper, and the interesting thing about it is nobody in the back gets out until the ones in the front leave first. So you can. The guys in the front don't get out, the guys in the back are in trouble.
Maybe one more, and then we'll have right here, and then we'll have some. So
You said they originally earned a negative connotation like Vulcan, but they don't do any harm. So what are they eating while they're adults that they don't do any harm?
So the adults do eat, and they feed on xylem fluid, plants as adults and as juveniles. The feeding doesn't seem to do any harm. The trouble is the female opposition in those live twigs. It weakens the twigs, and so you'll see an effect that we call flagging. Late in the summer, the ends of the twigs will die. This is not really a problem for the native hardwood trees here. The cicadas species are about 3 million years old. The tree species are old. This has been going on for a long time. They've all made their peace with it. The problem is if you run an orchard, it's going to affect your fruit set. And we have an FAQ on the website, all this business. The first sort of response is for people to go out there and spray tons of pesticides, which is in the end self-defeating because you cannot spray enough pesticide to kill all these cicadas. And in fact, if you do, you're going to kill everything, and that's not a good place to go. You have to physically exclude the females from your vegetation. If you have an orchard, You need to watch, and if you have cicada females coming into your orchard to lay, you need to wrap that up with avian netting as quickly as you can and keep that netting up for about 3 to 4 weeks. If you don't have cicadas, but you have an orchard, no problem.
Is there a reason that I've driven around a bunch of orchards and not heard so many there? Maybe it's rain over the years.
They may have been. There's also some issue with soil disturbance. Tilling it, digging it up, that can affect the nymphs as well. The cicadas may not be in the orchards, but they may find the orchards and go to them. So again, if you have an orchard, you need to keep an eye on it.
You guys want
I'll
to get these bugs jazzed up here?
I'll do that. You can answer. I'll give a spiel about this thing you may or may not see. And we're happy to take
Microphone
questions
on
as
the
well.
There we go.
You may see it. Keep your mic open. So these guys are on the verge of calling. What we're going to do here, these cicadas, in this case is a question of synchronization. The operational sex ratio in a magic cicada chorus is grossly biased. We think the actual sex ratio is 50-50, male-female. But because of the way that they work and their biology works, males mate multiply and are sexually receptive all the time and really trying to mate with anything that might even be remotely like a cicada. Such as a light switch. Females mate once, and they become sexually receptive at unpredictable times and locations. So that means that you think of the chorus as a little movie and look at it, little slices in time. In each slice, you have a situation where there are a gazillion males ready to mate and maybe one receptive female. And the outcome of that is they are very, very competitive. And the males will do everything they can to try to steal a mating or a courtship. So what I'm going to do, we have some cicadas that are on the verge of being ready to call for us. I am going to court myself. So I'm going to imitate a male call and a female response. And that's going to rile up this box of cicadas. And we'll get a male calling consistently. When he does that, I'll take over. I'll stop being the male. I'll let him call, and I'll respond to him. And we'll see if he'll go through the whole courtship sequence. This is always a bit of a dicey thing. These are morning insects. This is not morning. But we'll give it a shot. So. He's clearly listening. He's stopping. Turns out that cicadas don't seem to be able to hear when they're walking. So right at the time of that down slur, he's stopping. So he's listening. The question is, will he call? And actually, what he's interested in doing is feeding. So that actually does hurt slightly. They do not feed on blood, so it's a losing proposition all the way around. Again, he's stopping and listening. Didn't see that. Test the call once, and then he's all mine. But they don't like to do it in these circumstances. Do it for us. Good trick when it works.
You guys ever get arrested by the
He does. We have had some interesting conversations with law enforcement professionals over the years. And the bottom line is the sort of, you walk away and the impression is that they feel you couldn't possibly make this up.
Thanks. Bug music.
I have another question. Have you eaten them?
I have not.
You have.
John thinks it's a bad idea. He says they're toxic, 17 years,
Oh.
poison.
All right. Here's what I would say to that. Got a captive audience. You're going to see a lot of people with recipes and all that stuff about eating it. And here's the thing. I think that these cicadas are vulnerable. I think these populations are something we should be concerned about. I also think that to be a field biologist, you have to be in love with your research organisms. Otherwise, you would never put up with the things you put up. The combination of those sort of approaches to it caused me to think, I don't need to eat them for my own titillation and insight. The flip side of that, the more practical side, is there's a body of literature showing that they're mercury bioaccumulators. And I have enough holes in my brain as it is. I don't need to make more. So, no, I don't eat them.
But you do carry them in your mouth.
I don't swallow them.
How far do they travel in a lifetime?
That's a good question. And again, we can break up and do this more informally. They're really not very good flyers. They don't inspire confidence in their ability to fly long distances, and yet they've filled up all of glaciated North America in the past 10,000 years. So they have to be able to move impressive distances, and yet you throw them around and look at them and they don't seem like they're capable of moving 2 feet, let alone miles. So it's one of those intriguing questions.
Is there evidence of their presence prior to the last ice age?
Well, the species themselves, when you do molecular dating, it looks like the common ancestor of all 7 species was on the order of 3 million years ago. So they have persisted through several glacial cycles, and it's a good question as to which of the broods has persisted through the glacial cycles. The species, all except one, have. The broods? I don't know. We're working on it right now, and there's some Japanese researchers roaming around making the collections to do a more sophisticated molecular analysis.
Where's the best place to go hunting for cicadas like Terrabrissi for its balls?
I would say the Ulster County Fairgrounds.
Well,
lot of big meadowy parking lots where there's just, usually they go high in the trees, but if the trees are low, they can't go that high. So you have a line of trees, meadows on both sides, they're not that far away.
Along 299 going towards Mohawk.
Yeah, up there, absolutely.
oh
Yeah, on the corner of Mountain Rest Road and the road that goes along the wall.
Pine and Butterhill.
Yeah.
This guy's making this night
I have one here that this is the annoyance noise.
The-
Drop me, you're bothering me. We had a couple of questions about that. I mean, it's a good question. If you think about signals in communication, the mating signal, it's clear what the intent of that is. What is the intent of this? Is this an adaptation? And so the question is, well, if a bird picks this up and it makes a startling noise, maybe a bird drops it. And you do find there is some literature that shows over the course of an emergence, birds actually learn to drop these because they're males. They're giant gas bags. They're empty. Females are the ones you want to eat. They're the ones that don't make the noise. So this is annoyance.
Well, we'll let you guys sign some
There's one
books, I
question
think.
here.
I'm just curious, how deep is the soil? Do they,
All the old literature says that the nymphs are to be found up to 4 feet below the surface. And when we've gone digging, it's always 7 inches. Doesn't matter what time of year. You go in November, there they are. And most roots don't go that deep, and they're feeding on roots. And so they have some way of not being destroyed by hard freezes in the winter. It's a good question as to how they do that. We're happy to take lots of questions, but we'll break the formal portion of this up right now.